Hello, my dear students. Welcome to my YouTube channel, That's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the sp2 hybridization, that is, with one lone pair and two pi bonds in the structure. In the previous lecture, we have also done about the sp2 hybridization, but with an example of boron trichloride. And today we are going to take again sp2 hybridization with an example of sulfur dioxide, which is having one lone pair and two pi bonds in the structure. So today's example is sulfur dioxide. Sulfur dioxide, that's SO2 molecule. Before doing the hybridization, let's draw the Lewis structure of the SO2 molecule. So central atom here is sulfur, that's oxygen and the another oxygen. Sulfur, what's the atomic number of sulfur? It's 16. So the configuration will be 2, 8, 6. That means sulfur is having 6 electrons in its outermost shell. So we are drawing the 6 electrons. That's first electron, second electron, third electron, fourth electron, fifth electron and the sixth electron. Now let's talk about the oxygen. Oxygen, the atomic number is 8. So the configuration will be 2, 6. Here also the valence electron are the 6 electrons. So that means oxygen is having 6 electrons in its valence shell. So that's the first electron, second electron, third, fourth, fifth, sixth. Now let's draw the Lewis structure of the second oxygen. That's the first electron, second, third, fourth, fifth and the sixth. Now sulfur will form 2 bonds with the first oxygen and 2 bonds with the second oxygen. Now let's count the number of electrons, the valence electrons for the first oxygen after the formation of 2 bonds with the sulfur. So that's the first electron, second, third, fourth, fifth, sixth, seventh and the eighth. That means oxygen has attained an octet of 8 electrons in its outermost shell after the formation of 2 bonds with the sulfur. Now let's talk about the second oxygen. I am counting the valence electron of second oxygen after the formation of 2 bonds with sulfur. So that's the first electron, second, third, fourth, fifth, sixth, seventh and the eighth. So that means second oxygen have also attained octet of 8 electrons after the formation of 2 bonds with sulfur. So now let's count the valence electrons for sulfur after the formation of 4 bonds with 2 oxygen atoms. So that's first electron, second electron, third electron, fourth electron, fifth electron, sixth electron, seventh, eighth, ninth and the 10th. So this is the case of expanded octet where sulfur is having 10 electron in its valence shell after the formation of 4 bonds with 2 oxygen atoms. Why so? Why it is the case of expanded octet? Why sulfur is having 10 electrons in its valence shell? That's because sulfur is having extra 5 3d orbitals for the expansion of the octet, which we will study in the hybridization. Now, one more thing. Whenever there is a formation of double bond between two atoms, then in case of double bond, one bond will be sigma and the another will be the pi. So that means in this case, the double bond of sulfur and oxygen will have one sigma bond and the one pi bond. On the another hand, we are also having again double bond between the sulfur and the second oxygen. In that case also, the one bond will be sigma and the another one will be the pi. Now, before starting the hybridization, let me tell you one thing, that I'm again saying that hybrid orbitals only forms sigma bonds but not the pi bonds. And one more thing today I want to tell, that if any hybrid orbital is having two electrons with opposite spin, then that two electrons will be regarded as lone pair of electron. Now let's apply this concept in the hybridization of sulfur dioxide. Now in case of sulfur dioxide, in case of a sulfur dioxide, the SO2 molecule, the central atom is sulfur. The central atom is sulfur. Why so? Because sulfur is forming maximum number of bonds, that's 4 covalent bonds. That's why sulfur is a central atom, and we will be discussing about the hybridization in case of sulfur. Now, what's the atomic number of sulfur? Its atomic number is 16. What's the configuration, the valence shell configuration? It will be 3s2 3p4. Now in case of third shell, we are having three subshells, the S subshell, the P subshell and D subshell also, which we will be taking as 3d0. Now let's make the orbital diagram in the form of boxes. That's 3s. These three are degenerate orbitals of 3p, and the D subshell has 5 orbitals, and these 5 are degenerate orbitals of 3d subshell. So now let's fill the electrons according to the electronic configuration. The 3s is having 2 electrons, so 1 and the 2. The 3p is having 4 electrons, so we will be filling the 4 electrons according to the Hund's rule. So the first electron, second electron, third electron. Firstly, all the degenerate orbitals will get 1 electron each. After that, pairing will start. So now the fourth electron will come in the first orbital of 3p. So we got the first pair in 3p orbital. So we got the 2 electrons in 3s and the 4 electrons in 3p. Now let's come back to the Lewis structure. How many covalent bonds does sulfur is forming? It's 4 covalent bonds. Sulfur is forming 4 covalent bonds. That means in case of electronic configuration, there must be 4 orbitals containing 1 electron each. So only that sulfur will be eligible to form the 4 covalent bonds with the 2 oxygen atoms. Because I have already told you that 1 orbital of sulfur containing 1 electron and the 1 orbital of oxygen containing 1 electron, then they will overlap to form the covalent bonds. For the formation of 4 covalent bonds, we need 4 orbitals containing 1 electron each. So first of all, this is the ground state, and in ground state, 1 electron, the electron that have been filled in the last, will excite to the next orbitals. The last electron which we have filled in this electronic configuration is the 4th electron of 3p, which will excite from 3p to the 3d orbital. So we are going to make the excited state over here. So I'm again making the orbital diagram in the form of boxes. That's 3s, that's 3p, and that's 3d. Now let's just fill the electrons, 1 and the 2, 1, 2, 3, and the electron that have been excited from 3p first orbital to the 3d, it's over here. So now we got the 4 electrons in 4 different atomic orbitals for the formation of 4 covalent bonds, and this is called as excited state. Now after that, let's come back to the Lewis structure again. In this Lewis structure, how many sigma bonds are there? They are 2 in number. Out of 4 covalent bonds, we are having 2 sigma bonds. And I have already told you that hybrid orbitals only form sigma bonds. So that means during the hybridization process, or we can say during the intermixing of the atomic orbitals, we will take the 2 atomic orbitals containing 1 electron each for the hybridization. And during the hybridization, the orbitals available within the shell will be taken. So here in this case, one unique thing will happen, that we will take one s orbital and the 2 p orbitals for the hybridization process. So here we are taking one s orbitals and 2 p orbitals for intermixing, because shell starts from 3 s orbitals. So we will have to confirmly take the s orbital in each and every hybridization, because every shell starts from s orbitals or the s subshell. So we are taking one s and a 2 p orbitals. Why we have taken 2 p orbitals? Because in 2 p orbitals we are having one electron, which will form the 2 sigma bonds, and in the Lewis structure of SO2 we are having 2 sigma bonds. So that means 1s and 2p orbitals will intermix with each other. They will intermix with each other. That's called hybridization process. That's the hybridization process. So we are mixing 3 atomic orbitals, 1s and the 2p. So we will get 3 new atomic orbitals. 3 new atomic, or we can say hybrid orbitals. We will get 3 new hybrid and degenerate orbitals also, because they will be of equal energy. So we are going to have 3 new hybrid orbitals, because there's a mixing of 3 atomic orbitals, the 1 from s and the 2 from p. So 1s and 2p, we are mixing 3 atomic orbitals. The 3 new hybrid orbitals will form, and each hybrid orbital will be named as sp2, because it's a mixing of 1s and a 2p. So one hybrid orbital will get 33.33% s character and 66.66% p character. The second hybrid orbital will also named as sp2, and third hybrid orbital will also named as sp2. That means we are having 33.33% s character and 66.66% p character per hybrid orbital. Now, the three orbitals, the three atomic orbitals that we have mixed, we were having total of 4 electrons in them. The 2 electrons in 3s and 1 electron in 2p orbitals. So we were having total of 4 electrons. Let me show you. We were having 2 electrons in 3s and 1 electron in p orbital. So we were having total of 4 electrons. So they will be the redistribution of 4 electrons in sp2 hybrid orbitals. So we are going to fill that 4 electron according to the Hund's rule. The first electron, second electron, third electron, and the fourth electron in the first sp2. So now let's come to the first points that I have told you. If any hybrid orbital is having 2 electrons with opposite spin, then that 2 electrons will be regarded as lone pair of electrons. So that means in this case we got the lone pair of electron in first sp2 hybrid orbital. So that's our lone pair of electron. So let's come back to the Lewis structure. Which lone pair of electron? We are talking about the sulfur. So we got this lone pair of electron in hybridization. So that's our lone pair of electron. This lone pair of electron, these two electrons are present in one of the sp2 hybrid orbital. Now on the another hand, which atomic orbital we have left? Now we are left with one of the p orbital. We have left with one of the p orbital 3p containing 1 electron, and we have left with the d subshell which are having 5 degenerate atomic orbitals, 3d, in which one of the electron is present. Now I hope you are getting my point, that the 3s and 2 atomic orbitals from 3p have intermixed together to form the 3 sp2 hybrid orbitals. We are left with this 3p orbital which I have made, and we have left with this whole 3d subshell with 1 electron which I have made in the last point. Now let's talk about the oxygen. Now I'm talking about the oxygen. What's the atomic number of oxygen? That's 8. Configuration will be, valence electronic configuration is 2s to 2p 4. That's our 2s. And that's our 2p. So that's the 2s2 and that's our 2p4. Now oxygen is having 2 unpaired electrons in 2 atomic orbitals. Now let's come back to the Lewis structure. Oxygen is forming 2 bonds with sulfur, out of which the one is sigma and the another is pi. So that means here one electron will form the sigma bond and the another will form the pi bond. So let's take this in the hybridization. I'm taking the oxygen number 1. I'm talking about the first oxygen number 1. I'm making its valence electronic configuration of 2p orbital only. That's 2p. Now 2p is having 4 electrons, the 1, the 2, the 3 and the 4. Here one of the 2p orbital will have the head-on orbital. I'm repeating it again. One of the 2p orbital of oxygen will have head-on overlap with sp2 hybrid orbital of sulfur to form this sigma bond. So that's the sigma bond that have been formed by head-on overlap of sp2 hybrid orbital of sulfur with p orbital of oxygen. Now, on the another hand, the another electron of 2p orbital will have the sidewise or lateral overlapping with the 3p orbital of the sulfur to form the pi bond, and that pi bond will be between the 2p of oxygen and 3p of sulfur. So we got the p pi bond. This is also called p pi bond that have been formed by lateral or sidewise overlap of 2p orbital of oxygen and 3p orbital of sulfur, forming pi bond 2p 3p, which is also called p pi bond, because this have been formed between the side overlap of p orbital of oxygen and the p orbital of the sulfur. After that, now let's talk about the second oxygen, as we were having the two oxygen. Now I'm talking about oxygen number 2. Again we are having 2p orbitals of oxygen containing 4 electrons. That's first, second, third and the fourth. Now here also, one of the 2p orbital, that's the 2p orbitals, one of the 2p orbital of oxygen will have the head-on overlap with the sp2 hybrid orbital of sulfur, forming the sigma bond, and this sigma bond have been formed between, or the head-on overlap between, sp2 hybrid orbital of sulfur with the p orbital of oxygen number 2. Now here also again, the another electron from the another 2p orbital of oxygen number 2 will have a sidewise or lateral overlap with the 3d orbital of sulfur, forming the pi bond. So that means this pi bond have been formed by lateral or sidewise overlap between 3d orbital of sulfur and 2p orbital of oxygen number 2. So that's again the pi bond formed between the 2p of oxygen number 2 and the 3d of sulfur, and that's why this is also called p pi d pi bond. So we are having the varieties of pi bonds also. If a pi bond is formed between the p orbital of one atom and the p orbital of the another atom, that is called p pi, and if pi bond is formed between if the pi bond is formed by side overlap between the p orbital of one atom with the d orbital of the another, then that is called the p pi d pi bond. So here in this case we got the both types of bond, the p pi, that's between the lateral overlap of 2p of oxygen 1 with the 3p of sulfur, and p pi d pi also, that have been formed by the lateral side overlap between the 2p of oxygen number 2 with the 3d of sulfur. So that's about the hybridization. So now let's make the structure. As we all know, this is sp2 hybridization, whose structure is trigonal planar. But in this case, we are having the lone pair. So this name will be changed. So first of all, let's make the structure. We are having the sulfur, out of which the one sp2 hybrid orbital is having the lone pair of electron. That's the sp2 hybrid orbital, which is having the lone pair of electron. And after that, the sulfur, there is a head-on overlap of sp2 hybrid orbital of sulfur with the 2p orbital of oxygen. So that's the sigma bond between the sulfur and the oxygen, which will be formed by the head-on overlap of sp2 hybrid orbital of sulfur with the p orbital of oxygen. We are also having one more oxygen which have been formed by same type of overlap. So that's also the sigma bond that have been formed by head-on overlap of sp2 hybrid orbital of sulfur with the p orbital of oxygen. Now let's talk about the pi bonds. The sulfur is also forming the pi bond with oxygen. So this pi bond is formed by the lateral overlap of 3p orbital of sulfur with 2p orbital of oxygen number 1. So this is the p pi bond, and sulfur is also forming again one more pi bond with the second oxygen, which have been formed by the lateral overlap of 3d orbital of sulfur with the p orbital of second oxygen. So this is the another pi bond formed by the lateral overlap of 3d orbital of sulfur with the 2p orbital of oxygen. So this will be named as p pi d pi bond. So here we are having the lone pair in the geometry, so we will not consider the lone pair in the geometry, and this geometry will be called as bent shape. This geometry will be called as bent shape or V shape. So that's all about sp2 hybridization with one lone pairs and the 2 pi bonds. So one more point which I usually refer at the last, that's about the energies. Here we are having again two endothermic processes, the processes which are absorbing energy. One is the excitation of electron from 3p orbital to the 3d orbital, so that's called promotional energy. So that's the promotional energy that have been consumed. Promotional energy is consumed. And the another endothermic process is the intermixing of atomic orbitals to form the hybrid orbitals. So that's also the endothermic process which will consume hybridization energy. So here energy consumed is hybridization energy. So I am writing hybridization energy is consumed. Now at the last, there is a formation of 4 bonds, the 2 sigma bonds and the 2 pi bonds. The formation of bond is always an exothermic process. So I am writing here formation of 4 new bonds. The formation of 4 new bonds, that is 2 sigma and 2 pi bonds, is an exothermic process, which compensates the 2 previous endothermic processes, which compensates promotional energy, the endothermic process, and the hybridization energy, the another endothermic process. So as these two energies, the promotional energy and the hybridization energy, is compensated by the energy released during the formation of 4 new bonds, the 2 sigma and 2 pi, the formation of sulfur dioxide molecule is feasible or practically possible. So that's all for today lecture. I hope you all understood the sp2 hybridization with one lone pair and a 2 pi bonds in the main structure. So that's all for today. I hope you all understood today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then he/she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel with maximum number of students. Don't forget to press the subscribe button. Stay blessed.